Hi, and welcome again. So now we will approach Bayesian structural equation model. So just a quick recap. We are dealing with psychometrics, and right now we are dealing with validity evidence based on the latent structure. So now we need to create latent models based on a Bayesian perspective. So we will address structural equation models, that is a framework that encompasses confirmatory factor analysis, among other things. Okay, so structural equation models, just to be brief, require a theoretical framework. In this case, how many factors do you expect? Which items are the reflection of these factors? And other parameters like if you expect the factors to be correlated, or there is a correlation or regression with other things, or between residuals. So I will not cover path analysis and other applications of SEM regarding Bayesian structure, only confirmatory factor analysis, also called measurement models. Okay, and so remember that estimation methods can be complicated, and here's a really good algorithm that some colleagues created. Really good. Here's the reference on that. Okay, so once you estimate it with the chosen method, your model, you will get some fit indices. For example, CFI, the comparative fit index on the Tucker-Lewis index, TLI, that both should be above 0.90, RMSE-AA, the below 0.08, and SRMR, the standard raised root mean residual, below 0.06. These cutoff values are just from some standard references, but there's some debate on that, and there are advocates of using dynamic and adapted cutoff values towards your sample and your model and other values. Okay, so if you decide that the fit is satisfactory enough, you can describe the model that you have obtained. For example, examining the estimated loadings, the correlations between factors, its significance, etc. And if it's not satisfactory, you can check for modification indices. They are basically an index that says how much fit you would gain if you liberate this parameter that is restricted to 0. And if it has a theoretical explanation, you can include it. Okay, so if you want to make these models Bayesian, we first need to see which are the main priors that we need to make. For example, there are many parameters in these models, so we need to divide them by families. Okay, so for example, loadings are normally modeled by normal distributions. You can make them informative or non-informative as you like. Cross loadings also can be normally restricted to 0, but you can also change that. For example, for another normal distribution around 0, and loadings, for example, with a normal distribution around 0.4. EAM intercepts also have normal distributions along with factor intercepts and also regressions. But for example, EAM residuals normally have gamma distributions, also factor residuals. Correlations have beta distributions, also factor covariations have Wishart distributions. So as you can see, there is a lot more of knowledge that you need to manage adequately these distribution families. Okay, here are some a set of default priors or non-informative priors for a structural equation model, and also some informative priors, as you can see here, for intercepts, loadings, regressions, covariances, I think, residuals, and correlations. Okay, so whatever you want to try and wherever you have a selected prior list, an MCMC will start, and it can be very time intensive and also requiring much computation power, because as you can see here, there are many parameters to be estimated. Basically, each participant has a Bayesian inference on its factor score for each factor and everything that is behind: loadings, intercepts, residuals, correlations, regressions, etc. Okay, so once everything has converged and everything has stopped, you can check fit indices. In Bayesian models, we have a log likelihood model. Then you can extract a posterior predictive p-value. This is a value that can be analogous of a p-value of a chi-square. So if it's larger than 0.05 or 0.01, it's a good fit. And also you can have information-based indices like Bayesian information criterion, difference information criterion, the variance information criterion. This is the DIC. We also have the widely applicable information criterion and a very useful one, the leave one out cross-validation statistic. This is the preferred one if it's available because it's very robust. Okay, so all of these indices can be interpreted in the same way. Lower is better, but they are only useful if you have many models and you can compare them. In addition, recent developments have included Bayesian approximate fit indices that are basically making a Bayesian inference of a sampling distribution for RMSAA, CFI, and TLI, and with other more, for example, gamma hat, McDonald index, non-formed index, etc. However, the three that normally are used are the Bayesian RMSEA, Bayesian CFI, and Bayesian TLI. These three indices can be interpreted in the same way as regular ones or frequencies one, because they basically create a posterior, get to the maximum and a credible interval on that, so you can use them because they are obtained in a Bayesian way. Okay, now remember that thanks to the Bayesian update, we can compare many models with almost no type 1 error inflation. Therefore, you can be able to make some robustness analysis. There is no elegant way for doing this in a simple manner, for example, like in t-test or in ANOVAs. However, it's common to find some rudimentary form of robustness analysis, for example, starting with very non-informative priors for loadings, for example, and for example, with a normal distribution of around 0.4 and a standard deviation of 1, then another model for with 0.1 as standard deviation, then another model with 0.001, and then iteratively being increasingly more informative and see what happens to the fit indices, and then select the best model. Okay, so if you want to know more about information-based indices, here's a reference that can explain it. So yeah, that's normally what we normally do in Bayesian self-redundant fit. For all parameters that are being estimated, you will have trace plots, autocorrelation plots, effective sample size, PS or F, R hat, statistic, etc. So ideally, you should check them all to see if the trace plots are in a caterpillar form and the burning are okay, the autocorrelation plots to be okay, and the density curves to be similar, okay. But there can be so much parameters, even for simple models. So normally they are filtered by list. For example, examine only the loadings or the correlations or the intercepts and check if some problems might have occurred. Okay, so finally, if fit is not okay, you can check for modification indices that they are also obtained by a Bayesian estimate. So you can check for the posterior distribution of each modification index, then check for the standardized expected parameter change that will be estimated with MAP, EAP, or median with their credible intervals in that. And normally the EAP is recommended. Therefore, you can already check for a list of EAP values for modification indices and their credible intervals. Then you can get a PPP to test if this modification index is higher or lower than the observed one. Okay, so now you can get a filter list. For example, sort by EAP, filter the top rank, for example, the top 10 or the top 5, and select some candidates. Filter for the PPP, and also for the theoretical grounding that you can explain for that particular modification index. If you have, for example, 1 or 2, just include one of them, the best one, rerun the model and check if everything is okay and if now differences have been applied, and eventually if it increases. Then you can repeat that up for 3 modification index, just like standard recommendations, okay? Okay, so to wrap up, we can say that Bayesian SEM has some pros. It is more flexible than CFA because you can work with cross-loadings and other constraint parameters not necessarily as constrained. For example, you can make a prior of near 0 parameters and make an approximate cross-loading inference. And that's pretty good because maybe you can leave room for nuisance variations and really small cross loadings that can be damaging the fit from a frequencies perspective, and then get a really good structure going on with just some minor deviations going on. And because cross-loadings will be approximately zero, the majority of them, okay? In addition, an informed estimation of a Bayesian SEM can be done if we have good previous evidence, even if we have scarce previous evidence, because, for example, we can assume that the cross-loadings should be around zero, the loadings should be around 0.5 or 0.6 or something like that. And therefore, an informative model can be developed without many problems in psychometrics. This is good because you can work with small samples if you have a highly informative setting. And this enables to work, for example, in complex psychometric models when we have special populations or we are in clinical settings. In addition, Bayesian SEM can be extended to other frameworks, for example, dynamic inferences, etc. So how we can do these models? How we can compute them? So the main software I recommend is Blaban. It's a package in R that is the Bayesian expansion of Blaban. And it used to be JASP based, but now it's using Stan. And either way, it leaves you the freedom to choose whatever you want. There are plenty of materials from the maintainer that is called Ed Merkley, with YouTube videos with tutorials and also plenty of documentation. So I highly recommend Blaban. It's very useful, very exhaustive and comprehensive. However, the coding can be complex if you're not familiar with SEM or with Bayesian inference. And another great thing is that it is free and open source. The other contestant or the other good software to use is M+, because it enables you to use all of the same framework by yourself, including complex things like mixture models or growth models or something like that, and you can use that as Bayesian. The coding is less complex, way less complex. However, it is closed, it's not open source, and therefore you need to pay in order to use the software, and also you don't have access to the core functions. Okay, so if you want to know more about the technical details or more extensions to Bayesian SEM, here's the website of Ed Merkley. And highly recommend if you get a stride on that website and have a glance, because it is a really good documentation. You have also some tutorials on how to do Bayesian SEM, and also have more technical documentation in these two papers. So yeah, this is an overview on how to do Bayesian SEM.